Hi everyone. Today we are going to talk about the DOE and how to do analysis of variance using DOE. As we did in the last 2 weeks, we again going to look at 2 levels and 3-factor DOE, but instead of doing t-test as we did last week, we are going to do ANOVA analysis on that. So I'm assuming that you are now familiar with the 2-level factorial design, and I am going to go through the reading material that I have assigned in the Blackboard. This particular example is interested in making popcorn. Okay, so we have 3 factors, factor A, factor B, and factor C. Factor A is brand, which has the units of cost. You can either buy a cheap popcorn or a costly popcorn. Factor B is time in minutes, so this is the time that you spend in the microwave. It's either 4 minutes or 6 minutes. And then factor C is the power, which is in percentages, either 75% of power or 100% of power. Using these 3 factors, experimenters measure 2 outcomes. One is taste. Taste is a subjective test. After the certain factors have been utilized, the popcorn is given to a subject and they rated the taste from 1 to 10. And this is in percentage, what are the results were. And then the second one is a little bit more a quantitative outcome, right? This is the number of bullets. Meaning that number of popcorn that did not pop. And they measured in ounces. So you can see that from the same experiment that you can have one human-based subjective outcome and one more quantitative outcome. Okay, and this is our standard table. We have order 1 through 8. And then you also can say that they actually randomize their runs, right? So I will sort of invite you to read this part, why you should always randomize your order. And after building this table, they have then figured it out how to calculate the effects ABC and interactions AB, AC, BC, and ABC. And here's where the responses, and we got effect of 66.5. This is the average, right? So this is your 0 point of your cube. And you have the A had the effect of -1, B had the effects of -20.5, C had the effects of 17, AB had 0.5, which is pretty small, AC had -6, BC had 21.5, and ABC had 3.5. Okay, the ones that sort of get my attention here are 21 or 20.5, -17, and 21.5. I can do the same thing in my Excel sheet. So I'm just going to bring up the Excel sheet here. And you can see that the my responses were 74, 75, 71, 80, 81, 77, 42, and 32. And you can see that these are the same ones that we had in this PDF. So when you punch these numbers in, you can see that the average is 66, and we see that we get exactly the same effect. So you can replicate this table using the Excel sheet very easily. How can we figure out, without doing a t-test as we did in the previous week, how can we start figuring out which effects are important and which effects are not important? Okay, so the first thing that we'll do is something called half normal plot. Okay, half normal plot basically here, let me show you a half normal plot first. Okay, the half normal plot is basically half of a normally distributed curve, as you can see here, and it basically plots your effects from smallest to largest and finds out which are the ones that likely to rest outside of your statistical bell curve shape. So now what we do then is to order these effects, okay, from 1 to 7 in order from smallest to largest, and we use absolute values. And we will plot them against a cumulative probability from 7% to 92%. We have arrived to 92% by simply dividing 100 by 7, which gives us 14.28. And then we have taken the midpoint of that to 7.14. And we started from 7.14 and keep adding 14.28 until we reach to 92.86. Let's do this in Excel. As you can see here, I divided 100 by 7 and divided that to 2 to get the 7.14 and keep adding 14.28 to get to the 92. Highlighted here is the effects and the respective names. Let's sort them out. I will start by using custom sort time. Okay. I will sort both of these highlighted columns in the selected area. Okay, I'm going to sort it by column K, and I'm going to sort by values, and I'm going to sort from smallest to largest. And as you can see, it also sorted the names as well as this, so I can copy paste both. Now I don't need this, I can delete this. Okay, so now this is correct, and you can see that there's 4 of them that approximately follow a linear curve, and then 3 of them that fall outliers. So on the right side, these 3 will form our model parameters in the ANOVA analyses, and then these 4 is going to be the residual effect. If you want to plot for yourself, you can follow this PDF, but you can see there were 1, 2, 3, 4 that fall within the normal distribution. I was not able to draw this normal distribution, but if you have some sort of drawing tool or you are doing it by hand, you can easily do this. These 4 values roughly follow a linear curve, and then these values C, B, and BC are outside of that. Okay, let's go back to our model table to understand what these potential model parameters B, C, and BC mean and try to interpret these findings. A had the effect of -1, and we already know from our half plot that this will likely be non-significant. So that means that the brand did not have too much of an effect. B was time, and increasing time had a minus effect on taste. That means that more we cook these popcorn, the taste got worse. So that's one thing. And C was power, and likely the more we increase the power, taste also got worse. Okay, so that means that both the time and the power of the microwave is associated with decreased taste. When we looked at the interactions, the only one that stood out was the BC interaction. And we can readily see that the BC is the interaction of time and power, and it also had a minus value. So if we were to try to interpret these findings, I would plot something like this. Okay, I will plot the taste, which is the main outcome. These are the values, right, from anywhere between 30% to 90% in this graph. And B is, as you know, is the time. So it's in minutes. We cook them anywhere between 4 minutes to 6 minutes. And C was the power, okay? So the C plus is here high power, C minus is low power, and the low power was 75 and high power was 100% power. You can see at 4-minute cooking time, both 75% power and 100% power produce the similar amount of taste. So that means that the power had the similar effect, right, at 4 minutes. At 6 minutes, low power had a little bit of an effect of increasing the taste. So that means that if there were some popcorns that was not cooked exactly, they started to cook, so the taste was improved slightly, although this was probably a non-significant increase. But in high power, as we increase the time, there is a significant decline in the taste. So that means that your popcorn is likely started to burn as we increase the time with the high power, right? So by looking at these interactions, that we can say is that we either want to cook it at high power with low, right? Or with the low power with the high time, but not high time, high power, or not low time, low power. So that means that this gives us an interpretation of ideas of how our system parameters or how the factors that we choose in affect the measured outcome. So let's look at how can we use ANOVA analyses to figure out the significant effects in these type of factorial designs. ANOVA, as you remember, is the calculation of F ratio, okay, and that is then calculated or compared against the F critical value. In this case of ANOVA, in two-factor, three-level DOE, before we start ANOVA, right, we have done our half normal plot. And what happened was that the here's the half normal plot. We had 1, 2, 3, 4 effects here, and 1, 2, 3, 4 effects, 4 effects in here, 3 effects in here. These 3 effects were call them main effects, right? Were B, C, and interaction between BC. And the residual effects, which were these 4, right, are A, AB, AC, and ABC. Okay, so this is a preliminary analysis. In other words, we are thinking that these 3 are likely the ones that are significant, and these 4 are the ones unlikely to be significant. So to calculate this, to put to a test using analysis of variance, we are going to have to calculate the F ratio for the model. Okay. And for this model, we are going to use the, again, effects of B, C, and BC. This model is defined as F ratio is defined as mean of squares model divided by mean of squares residual. Okay, and that's defined as the sum of squares model divided by degrees of freedom model, and that's divided by sum of squares residual divided by degrees of freedom. In this case, sum of squares of model is defined as the sum of squares B plus sum of squares C plus sum of squares BC. Let's calculate the sum of squares B, for example. Sum of squares B is given as the n, which is number of runs. Let's write this. Number of runs divided by 4 times the effect of B squared. So in that case, this will be 8 divided by 4 times minus 20.5 squared. This will give us a sum of squares value of 840 0.5. If we do the same things for the other effects, we will find that the sum of squares model is 2343. Sum of squares residual is then given as 99. Our degrees of freedom for the model, okay, is 3 because we only had 3 effects, and degrees of freedom of residual is given by 4. You can imagine our DF model in here is going to be new 1, and our DF residual is going to be new 2. MS model then is given as the SS model, okay, divided by the F model, okay, and our MS residual, okay, is given by the SS residual divided by the DF residual, okay. And if you calculate the F ratio by the MS model divided by MS residual, that we will find that it is 31.5. What is F critical? Okay, the F critical is defined by two values, right? In this case, I can highlight them by DF model here, which is new 1, and the DF residual, which is 4 here. So if I were to go back to our original table that we have given, you can see that the for new 1, if you go to our column number 3, and for new 2, if you go to row number 4, we'll find that it's 6.591. Okay, so for 95%, it is F critical at 95 percentile is going to be 6.591. Okay, so we can say that the F ratio is bigger than F critical. Okay, so that means that the model, okay, has a measurable effect. So we found that the model sum of squares was 2343, the degrees of freedom was 3, and our residual was 99 and degrees of freedom 4. And in that case, we made the conclusion that the model had a significant effect, less than 0.01. So I will also show you the data here. So this is a ANOVA sort of distribution chart for model of 3 and residual of 4. As you can see, the 10% is 6.59, which is what we found from our table. For 1%, it is 16.68. The 31.5 was the value that we have found for our F ratio, and 0.01% was 56. So that we can say that our model in every case was less than 1% chance to observe this effect. So in that case, we can conclude that the probability was less than 0.01. Okay, and we can do the same thing now for each effect one by one. So if you do for effect of B, C, and BC. The only difference is that the residual is going to stay exactly the same, okay, as it did before. But the degrees of freedom for BC and BC is going to be 1, so that will be a different calculation. But you will get the F values of 34, 23, and 37.3. In this case, we will go for 1, okay, and 4. So our F critical value becomes 7.7 up from 6.59. This is only for 5% significance. If you go down for 10% significance, you can also look at those values. And if you can go to 1% significance, you can also find those values as well. So anyway, you can figure out what is the probability level, what is the p-value. And from there, we can calculate whether the model is significant. And you can also calculate whether each effect is significant. So it is possible that the model is significant and B and C was significant, but BC was not significant. So that's a possibility, and you should check all the model parameters one by one. So what happens if you found that, let's say, B was significant, the C was significant, the BC was not significant? This BC then will become part of the residual, and then you'll recalculate your table. In summary, we had 12 steps to run through. First, we have calculated our effects using highs and lows. We have then sorted them for the absolute values in ascending order so that we could do a half normal plot. And from half normal plot, we have determined two things. We determined the residual parameters most likely, and we have calculated the model parameters. Using the residual and model parameters, we have calculated sum of squares as well as the mean of squares and degrees of freedom. Using tables, then we constructed our ANOVA table, and using statistical tables, we have figured it out what are the p-values for the main effect or the model, as well as each individual effect that we have identified. We have also talked about if an effect was not significant, we can roll that back into the residual effects and recalculate. We have also went through plotting the main effects and their interactions, as well as interpreting the results.